the earthquake sources around Malaysia. So these are, when you conduct the study, you will do this earthquake sources based on the location. I think I should go faster because it's already 30 minutes. Okay, the case study here, for my case study, the location is in Peninsular Malaysia. The facility that I'm going to share is in Peninsular Malaysia. So it's located here. So it's important for me to check on the surrounding region. What are the potential earthquake events that could produce future, that could, what are the potential earthquake sources that could produce earthquake events towards my location. So most of it is coming from far field earthquakes in Indonesia, plus the local earthquakes, small earthquake in Peninsular Malaysia itself. Okay, so here is the fault identifications at the local area of Malaysia. So the one which is identified very close to the area of the facility is Bukit Tinggi fault line. So we are doing some remote sensing analysis to find all the informations of the fault lines, how active is the fault line movement, and what are the active events, earthquake events happening around. And another work can be done is fault verification. This is also another activity to see whether it's the right thing that the faults are in that region. So this is on-site activity. Okay, another factor that you will need in order to conduct the seismic hazard assessment is ground motion prediction equations. So in this case, we are doing a lot of analysis to find what is the best GMPE, ground motion prediction equations, for the location of Malaysia. So we are using most of it Atkinson and Bohr, Zhao and et al, Shishtari. Yeah, these are among the best, the closest GMPE with the real events that happens around Malaysia. So you can see here, there are 3 zones: Sumatran Fault Zone, Sumatran Subduction Interface, and Sumatran Subduction Intra-Slab Zone, and also the local faults. Okay, so from the processes that you follow in seismic hazard assessment, you are able to produce seismic hazard map of a country. So in this case, the team of Mineral and Geoscience Malaysia, Department of Mineral and Geoscience, plus Department of Standard Malaysia, they have produced the final seismic hazard map in 2017. This is for Peninsular, Sarawak, and Sabah. So I am very much actively involved in this project. So I'm showing to you the seismic hazard map for Peninsular, where the case study area is located. And this map is for 10% probability of accidents. When we are doing assessment for industrial facilities, that is critical. So you should go for 2% probability of accidents, which responded to 2,475 years return period. So it's a longer period, meaning a higher peak ground acceleration will be imposed to the structure. Okay, the first part is done on seismic hazard. So now you will have to continue on the second part, which is site-specific ground response analysis. A lot of studies has been done everywhere, especially in India, in Malaysia, everywhere in this world. So it's so a lot of guidelines are there. Okay, so many softwares available. You can use Shake 2000, Deep Soil, any method that is suitable for your location. So basically, the procedures for seismic hazard is you will need the data from boreholes, because you're going to check on the size on the shear wave velocity. If you look at this graphic representation, the way we check is from the earthquake itself, the seismic source identification. It will bring some waves, yeah, to the bedrock. I mean, to the bedrock of the beneath the site. So from here, from the bedrock, we're going to check on the amplification when the shear waves are propagating into the ground surface. So the ground surface in every area are normally very different. So it depends on the type of soil and also, type of soil, very much on category of soil. So from this analysis, we would be able to understand what is the soil amplification of the shear wave that will be imposed to the structure on top of the soil. Okay, so in this case, my case study, the peak ground acceleration at the surface was found to be around 0.15 G PGA to 0.2 G. Okay, so I'm going to use this value to evaluate the structural assessment of the buildings. So these are the input data for seismic response, ground response. You will need boreholes data, as much as possible boreholes data for one location, if you can get, yeah. And you also need time history analysis. So if let's say we don't really have accurate time history at a specific location, you could also use the one which is from other locations, but to be matched with the target response spectra and also to be matched with the characteristic of the specific location. On the results part, this is the most, the results of site specific will give us some idea on the predominant frequency zone of the soil in that area, and then how much is the amplification of the soil in that specific site. And most important is this design response spectrum. Okay, so if you see the figure at the bottom, I compare the original analysis with, if let's say we are only using values from Eurocodes, you're taking values from Eurocode, it is so much different. See? Eurocode is giving us a very smooth to the left, very rigid. But the real situation is actually it's being shifted to the right, which is longer period of the building. That is very true because the condition in Malaysia is subjected to long distance earthquake. Okay, the case study I'm going to share with everybody is on this Sinagama irradiation plant in Peninsular Malaysia. We could do this type of assessment to any facilities, which based on whatever data that are available. So in this case, this facility is owned by Malaysian Nuclear Agency, in operation starting 1989. So we know that the building here is a moment-resisting reinforced concrete frame. It has steel portal frame attached to exterior RC column. So what is this industry doing? The plant is using ionizing energy from gamma radiation cobalt-60 source to irradiate products like doing sterilization of medical products, pharmaceutical tissues, bones, and so on. Yeah, so it's a very important facility in whichever country. Yeah, so we have to ensure that this type of facility is always safe toward any hazards around, possible hazards to occur in the area. This is roughly the figure of the site of the industry. And this just a diagram of it. And on the right hand side is the layout of the industrial building. So the main facility is located in the vast big area here, big free area. And the front part are just the offices rooms. Okay, so the third section is we are going to conduct vulnerability assessment of this industrial building. So normally a vulnerability assessment is it's a normal exercise that engineers do to assess buildings. You could use the same approach to also assess on normal buildings, high-rise buildings and so on. So it's just that we are taking consideration about industrial building because it has a very long span and they are normally made of portal frame. So we have to check on the response, the performance of this building with earthquakes. These are some of the layouts of the portal frame. So it has here RC column with the attached portal frame, steel portal frame. Okay. In my study, I'm using damage index that is based on global period based damage index. Yeah. So these are some of the information being used, the parameter. So in many studies available, there are many damage index parameters that can be used. Okay. All right. So finally, our aim is to come up with the vulnerability assessment where you can come up with mean damage ratio with peak ground acceleration. Yeah. So here we could see at 100% damage, the building is with capacity of 0.75 G. So to us in Malaysia, 0.75 G is a very high capacity because the earthquake, we could see the demand is just about 0.2 G for Malaysia case. Okay, so it seems that the buildings, of course, the building has been constructed well because they know initially that it is for high importance. So I'm sure that's the main reason we found that the capacity is very high. So from vulnerability, you have to develop the seismic fragility curve of the industrial building because we want to combine this with the industrial facilities assessment in the form of fragility curves. Yeah. Okay, so here in the form of fragility curve for collapse prevention, the red line, collapse prevention, it's giving us mean acceleration capacity of 0.68 G, slightly lower from the vulnerability, of which we can use this value for the next step. Okay, the last part is seismic probabilistic risk assessment of industrial facilities. So this part is very important because this is where we can look into in depth about the performance of the facilities, equipment itself. So they consist of preliminary industrial facility system analysis. Then we go for fragility evaluation. The next part is structural and system reliability assessment. Last, then we can calculate the seismic risk. Okay, so in the first step, preliminary industrial facility system analysis, the best thing is to do plan walk down. We have to go to the site, we have to look at the site, do inspection, because from the walk down, you are able to see the real condition, yeah, and also verify what is in the design plans, you see, to check on the accuracy of the system description. And you could also conduct a second walk down or third walk down to collect more specific data and to see the critical components, yeah. And you will be, after a few visits, you will be able to get more data, more more information about the potential of seismic weakness in the existing facility. All right. So during my walk down in this facility, some of the pictures I'm showing here. So I took just small pictures here. I'm sharing with everybody. So these are the normal industrial equipments, mechanical parts of it. These are the pipes, cooling system here. We have this monitor, outlet monitor. This is part of the conveyor belt, yeah, where the boxes are going through this conveyor belt into the irradiation room for the irradiation process, and it will come up on the next slide. So you can see from the walk down, you will be able to see what are the parts being attached to the building? Are there any parts of the facility attached to the building, or are they sitting on its own? And then, and a lot more information. Okay, so this is varies according to each facility. So information data is very, very crucial when we conduct this study. So once you get all the information, you have to sit down and then categorize things into major systems and critical components. These are the assessment that should be done. You will categorize. So in my case, in this case, what we did is categorizing it into we found 5 major systems: radiation shield bunker, the source storage pool cooling system, the gamma radiation source mechanism, the product or material handling system, and also the source storage pool. So a lot of components involved here in every category, and you're trying to look at the categories of equipment, whether they are structural, restrained, non-restrained, minor, passive, and so on. Yeah, a lot of the guidance can be found in papers or books related to industrial facilities. So this is very much related to mechanical information and also on risk assessment. So from here, the next part, we will try to find what are the auxiliary systems. So we know auxiliary system, sometimes there are redundant, there are many of them. Okay, so there are also components involved, and normally auxiliary system could fall under non-critical category. Right. So an example here, I'm showing here on seismic failure mode in the pool cooling system. So this is the system of cooling system of the facility. There are a few items involved. There's a few components involved in here. So it becomes one pool system. So every component will be identified, and we are trying to brainstorm, trying to investigate what are the potential failure modes. So the potential failure modes information can come from the operator of the facility himself, because he has been dealing with the facility and a lot of incidents has happened before, or incidents in other locations related to the same facility can become information for the potential failure mode. Yeah. Okay, so next, I'm showing the seismic initiating events. This is example. I'm showing just 2. So the first one, we identified seismic initiating events. Let's say a collapse of industrial building. So if the whole industrial building collapse, what will happen? So among the systems that are affected will be radiation shield bunker, the pool cooling system, the source storage pool system, and also the generator set room, which is fall under this initiating event. So potential seismic failure modes are listed here. Okay, so from these events, we can do assessment to give factor of safety of each of this equipment, and how much earthquake capacity it could hold for the facility itself. So this capacity, you can refer to industrial assessment books, and we have many methods available. Starting in 1989, Kennedy and Raudhah has been also showing a lot of analysis on nuclear power plant, chemical plants. These are among the most critical industrial facilities where studies of seismic failure has been done. Not much on the common recent industrial facilities. Normally, the previous studies are more on very critical facilities. Okay, so a lot of information needs to be obtained. Second here, in seismic initiating event, let's say there's a multiple piping system failure. So what are the subsystem affected? So we identified source storage pool cooling system, ventilation, air compression, and water deionizer, and so on. Okay, so you can read this. Okay, so apart from, you see, the previous one, seismic failure modes here, the assessment is done based on a factor of safety. So in addition to that, I think finite element modeling these days is capable to analyze what is the capacity, earthquake capacity of each particular equipment. So therefore, in here, I'm expanding to with my students, my final year students, research students. They are doing some modeling, finite element modeling, to understand further on the response of the bunker, and also on the source storage pool cooling system. Yeah, some of this. Yeah, these analyses are ongoing. So here you can see the flow chart is telling us what are the processes that can be involved. Okay, so I think a lot of us are familiar here with this Abacus software modeling, finite element modeling. We are trying to find displacement as the parameters, displacement, the peak ground acceleration response of the components, and the last part is on the system level. Okay. Okay, coming back to the framework, the process of seismic risk assessment, we also need to find the seismic initiating events. Okay, I think this one is shown just now. So collapse of industrial building, so radiation shield, pool cooling system. Yeah, I've mentioned this. Okay, so once I've chosen, for example, I have chosen this collapse of industrial building out of the whole system in this facility. This is found to be the most critical. So you will bring this further into probabilistic analysis, statistic analysis. You can do a lot of statistical analysis. In my case, I'm using fault trees analysis to look at the subsystem. Yeah, when these systems are overlapping, yeah, which one is the most critical? And from fault trees, you will move further into event tree analysis to come up with the possibility of each event, yeah, each failure. So here, sequence designation are the potential failure mode. Okay. All right. So from that event tree analysis, you produce fragility curves. Yeah, fragility curves. Fragility curve is just to show us the capacity of the equipment, and also the potential of failure that exceeds the probability of failure, which exceeds certain peak ground acceleration. Okay, so these are all very probabilistic method. Okay. In this process, this is a process being normal, being done in industrial facilities risk assessment. So I'm following the similar approach. Okay, so you follow subsystem initiating events, and finally the event sequence. So trying to find the final probability quantification. And from there, we will be able to combine the whole probability of risk into fragility curves. Okay, if you look at the red line is the plant fragility curve for high seismicity. Okay, and in the real case, okay, the red line is the real situation now for the facility that I am assessing. And the hazard in Malaysia, you see this dotted vertical line is showing the upper limit for seismic hazard in the case study region, meaning the hazard is very low, and as if the facility is very, very safe. Okay, so therefore we created another case when, let's say, the facility is badly constructed. So if it is badly constructed, it shows that there will be risk. Yeah, there will be risk, and there will be a calculation of risk. So the black line here, fragility, I'm using the this black color line, fragility, just for the purpose to calculate the seismic risk computation. If I don't make it badly, meaning there's no risk at all. But if there's no risk, if you compute risk computation, the value is 0. Okay, so this is an exercise to compute seismic risk. So from the fragility curve that we uh, obtain, we will further calculate seismic risk. Seismic risk basic formula is annual hazard multiply with fragility, and you could multiply with the remaining life, multiply with the consequence of the values in terms of monetary. Okay, so overall, it will be in the form of probability. This the one I'm showing here is a combination of annual hazard. Okay, the first column is hazard, second column is fragility. Sorry, this part is fragility. The remaining life is just 40 years, and that's it. Consequence is just a monetary value. So this 1.29 to the power of 10 minus 3 per year is the annual frequency of unacceptable performance. That's a specific formula for you to use. You can try, you can look further into this equation if you wanted to know more. So in this case, as an estimation, it's a £500,000 to be the risk of the building. If let's say the structure of the building collapse, okay, because that was the prediction, that was the weakest point. The rest are all having high capacity. Right, as a conclusion, so when we study seismic risk assessment, you will want to find the direct loss. So the direct loss is to be found as how I showed to you the calculation. And we know in the indirect losses, in this case, is normally for Sinagama irradiation plant, we are afraid the adverse effect of the radioactive substance release to the surrounding areas. We also fear that the plant downtown and business interruption could happen. It will affect the business reputation with significant long-term loss. And we know usually the loss is 3 times larger than the direct loss. Okay, so total loss here, I'm leaving it as empty because it is not an exact value. Okay, so we know business interruption cost is normally 3 times the cost of physical damage. So that is a very unacceptable loss to industrial facilities. All right. So I think that's all on my presentation. I would like to convey my gratitude also to the Malaysian Nuclear Agency for supporting me in terms of the data for this research. Also to the Ministry of Higher Education Malaysia and UNIMAS for the financial support. Last but not least to the University of Sheffield, because that is where I did this study. Yeah. Okay. So any question? Yeah, I think it's time, yeah?
Yeah, actually, ma'am, there's one question.
Uh-huh.
First of all, thank you very much for such a fabulous and wonderful lecture. So,
Thank you.
I'll read few questions. First is, how reliable are prediction for seismicity?
Okay, for seismicity.
Yes, ma'am.
Yeah. Of course, the perfect prediction is never been there. Of a lot of studies has been done to try to find a very accurate. You know, everybody is trying to move towards a very accurate, but as in the form of seismic risk assessment, since we're using probability, as long as we stick to a very close assumption, reduce the uncertainties, it would be with high reliability. For example, in 2008, Wenchuan earthquake, you see, China is very prepared with seismic reliability assessment, seismic hazard assessment. So they could already, closely predict where seismic is going to happen in Wenchuan. So they have moved the population from that area, and the earthquake happened in 2008 Wenchuan. So a very low loss of life happens. But unfortunately, they could not remove the industrial facilities. So at least they save lives, you see. So therefore, we would say a seismic hazard assessment has a high reliability so long as the data is very enough, enough data and prediction use, assumptions used with reduction of uncertainties are there.
Ma'am, I have a question.
Yeah.
Yeah, actually, I have two questions. First question is related to the microzonation.
Okay.
So, my question is that whether you have done the soil investigation to achieve the microzonation, because the attenuation relationships, as far as I know, cannot be prepared without soil investigation. So, this is my first question.
Yeah. Okay, so yes, soil investigation, uh, it depends on locations, you see. So in my case, the only information for investigation comes from this boreholes data for the exact site. Okay, this is more to site-specific analysis. But when you want to do a micro-zonation for a bigger area, you need to have a lot of boreholes data, which is distributed nicely. So you could come up with contour lines, yeah, contour lines that could show the a better representation of peak ground acceleration response in that area. So in the case of industrial facilities, normally we will make do with information such as boreholes data in that specific area, small region. So both data is more or less the only information for my case. But of course, you could conduct tests. You do sampling. If there are more more in-depth, deeper boreholes data that can be obtained, that is nice. But most of the time, we are obtaining boreholes data from construction. So when construction area, normally the depth is not more than 30 meter. So you have to just utilize the formulas and equations available, yeah, to reduce the uncertainties.
Okay, thank you, ma'am. My
Yeah,
second question is regarding fragility curves. You have to perform some kind of analysis, whether nonlinear dynamic analysis or incremental dynamic analysis,
true.
before creating the fragility curve. So, what kind of analysis you do on the industrial components before fragility analysis?
Okay, so I did just write down there. It's pushover analysis and also time history analysis. These are the two nonlinear approach that we use. That is common normally people do.
Okay, so directly on the basis of these nonlinear analysis, you uh, jump over to the fragility analysis.
True, and
Yeah.
you have to verify all the parameters. For example, if you are applying whatever configuration, you have to make it probabilistic. In my case, I'm using Monte Carlo simulation to make a bigger range of uh, parameters values, and so that you cover all the uncertainties to come up with the final fragility curve. Yeah, because fragility curve also involve a lot of you have to consider a lot of possibility of values to be assessed.
Okay. Thank you so much, ma'am.
Yeah, no problem.
So thank you very much for this fabulous and wonderful webinar, ma'am. I
Oh,
think
no problem.
all the participants have learned a lot, and they have a new vision about the seismic risk assessment in Malaysia. So thank you very much, ma'am, once again, and I welcome Dr. Rana Patak, ma'am, to have a welcome word of thanks to Raudhah, ma'am.
Thank you, Dipen sir. It's my pleasure to thank Dr. Ahmadi. It's our pleasure to listen to your talk, and it was very wonderful. Your presentation was very nice. It was very informative, and I have seen the participants. Many of the structural engineers and research scholars pan India have joined your webinar. So it should definitely very fruitful and informative for all the participants. So we look for the collaboration with your university in future also. Thank you very much for accepting our invitation. So on behalf of Sri Vaishnav Vidyapith Vishwavidyalaya, I thank you from the bottom of my heart for accepting our invitation and preparing this presentation for us and sparing your valuable time for us. Thank you very much once again, ma'am.
Thank you, Dr. Rana, and also thank you, Mr. Dipendra. I also thank the head of department once again, and also the director, Dr. Namit Gupta. Yeah, thank you very much for inviting me. This is a great honor for me to share internationally my research area, and I hope for further collaboration with everybody. Um, and from UNIMAS, University of Malaysia Sarawak, my faculty, the head of department, and the dean, they are also delighted to for me to present here and have this collaboration with Sri Vaishnav Institute of Technology and Science. Thank you very much. Yeah, hope to see you guys to come in Malaysia and join UNIMAS maybe for masters and PhD studies.
Sure, ma'am. Sure, we
Yeah,
will
you guys are
definitely
welcome.
meet. We would like to have you in person also when this pandemic is over. We would
Yeah,
definitely invite you to our university. That will be one more opportunity for you also to come to India again.
nice, nice. Thank you very much. So see you in Malaysia maybe one day. Yeah.
Yeah,
Okay.
sure. Okay, ma'am. Bye
Thank you very
Thank you,
bye.
much.
ma'am.
Take care.
Bye.
Okay, take care. You too.
Yeah.
Bye.
Bye.